A prestigious Nobel Laureate cautions us that the James Webb Telescope has simply found something odd in the universe, and we may not be prepared for the progressions that are coming. The most recent disclosures present difficult issues for our science. It's getting more insane and more insane on the grounds that, once more, James Webb has found a totally new peculiarity that is turning our material science course readings topsy-turvy. Astrophysicist and Nobel Prize victor Adam Rees has long thought that mainstream researchers are heading for calamity. Scientists report heaps of inexplicable riddles that are becoming more prevalent each day. Might we at any point actually grasp the circumstance, or is our science at an end? Adam Rees is likely an exception among scientists, keeping a composed mind these days. Since the launch of the James Webb Space Telescope, nothing is as it used to be. The universe is probably much older than previously accepted. Galaxies have formed much faster and uniquely in contrast to our forecasts, and our universe may not be expanding from a single point. What happens now, assuming that dark matter is potentially still an error and James Webb is now introducing the next picture of puzzling peculiarities in the universe? Adam Rees is one of the leading specialists in the field of research into the expanding universe. His contribution to the discovery of the accelerating expansion of the universe revolutionized our view of the universe's extension and was one of the foundations of the Hubble fervor. Rees welcomes the telescope's most recent revelations since he knows from his own years of dedicated work that our cosmology is flawed. He was involved in reviewing the universe and utilizing supernovae as standard candles for the first time. In this context, standard candles are something like cosmic scales that researchers use to gauge movements and distances in the universe. By using supernovae as a measuring stick, incredibly exact measurement results could be achieved. Yet one issue remained. Rees and his team found that the expansion of the universe was increasing regionally rather than uniformly. During their work, another peculiarity became evident as Rees's measurement results differed fundamentally from those based on the redshift method. This shouldn't truly be the case. Today we know the differences in the measurement results as the Hubble tension. Rees's work was so marvelous that he was awarded a Nobel Prize in Physics in 2011, along with his associates Saul Perlmutter and Brian P. Schmidt. He received the award for the discovery of the accelerated expansion of the universe. Rees and Schmidt are members of the High Z Supernova Search Team, which is investigating methods to refine the measures of distance in the universe. Perlmutter, on the other hand, reached similar conclusions at around the same time as part of the Supernova Cosmology Project. They observed Type Ia supernovae, exceptionally bright exploding stars that act as solid indicators of distances in the universe. These observations provided compelling evidence that the rate of expansion of the universe is increasing rather than diminishing due to the gravitational effects of matter in the universe, as previously thought. The isotropic universe, the greatest crisis in modern science, was gradually brewing, and now the bomb has detonated. Instead of answers, astronomers and cosmologists are constantly being presented with new riddles and surprises. Nowadays, the idea of an isotropic universe is also on the verge of collapse, and with it, one of the major pillars of our cosmology. Isotropy assumes that the universe looks the same in all directions, regardless of where you observe it from. This supposition is a fundamental part of the cosmological standard, which states that the universe is homogeneous and isotropic on a large enough scale. For instance, the cosmic microwave background radiation pattern looks consistent all over, and large clusters of galaxies are similarly distributed across space. Essentially, that is how it used to look, and researchers turned these observations into essential mathematical rules to simplify scientific descriptions of the universe. Yet, this may have been a significant error. The observations of
Adam Rees and other researchers exploring accelerated expansion initially confirmed the isotropic model to some extent because the measurements of supernovae showed consistent results regarding the rate of expansion. This means that there appears to be some form of isotropy. However, the expansion is much faster than it should be according to old physical assumptions. The end of dark energy remains a significant challenge in science. To understand the riddle of the new cosmology, we need to take a closer look at dark energy. The exact nature of this energy is still unclear, but its presence and properties are crucial if we want to understand how and why the universe expands in an isotropic manner. Dark energy is a theoretical form of energy that could be present anywhere in the universe and likely plays a key role in current theories about the universe's expansion. It is thought to be the driving force behind the accelerated growth of the universe by acting against gravity and pushing the universe apart. In current cosmological theory, dark energy is responsible for around 68% of the total energy content of the universe. Here you can already see a problem. Researchers attribute almost 70% of the energy processes in the universe to an energy whose presence has never been proven. A significant component supporting the presence and properties of dark energy up to now was the observation of type Ia supernovae, as done by Adam Rees and associates. The accelerated expansion observed here couldn't be explained without the influence of an enormous force. Additional evidence that this mysterious energy truly exists was provided by the cosmic microwave background radiation and other large-scale structural studies. However, recent observations by the James Webb Space Telescope have now shaken the concept of dark energy. The JWST can observe the early universe in a degree of detail that was previously impossible. Even the first precise observations revealed structures and objects that are older and more developed than they should be according to the standard model of cosmology. These observations could indicate that the universe may have expanded significantly faster or began at an earlier time than previously thought. All these results suggest that we have not yet understood some crucial components and forces in the universe, including dark matter and dark energy. It is likely that we are now facing a complete revision of the standard cosmological model, but we are not ready for that right now. We can't develop new theories because we don't have enough concrete data about what's going on. Will we find the answer in the realm of particles? The upheaval in our understanding will need to wait a little longer. Only when Webb gives us more images and scientists make even more incredible discoveries can we piece together a new picture. That might take time. Meanwhile, analysts around the world are searching for answers that are already available. David Gross is another researcher who welcomes the crisis and sees it as an opportunity. Gross points out that the answers to the great mysteries of the universe are not hidden in the universe but in the microcosm. The famous theoretical physicist is an expert in the theory of strong interaction and string theory. He is also a Nobel Prize winner, receiving the honor in 2004 for the discovery of asymptotic freedom in the theory of strong interaction. This discovery was fundamental to understanding the behavior of quarks, which are the primary building blocks of protons and neutrons. These particles are the main actors in the standard model of particle physics and form the basis of everything we can see and measure in space.
Therefore, the basic structures and principles of the cosmos must also have counterparts in the subatomic realm. The concepts that Gross helped to develop explain, among other things, the situation immediately after the Big Bang. He realized that there were no stars and no objects in the universe at that time. For millions of years, there was only a very hot primordial soup in which particles moved freely through space without forming bonds. Before the Big Bang, there was probably only a kind of quantum fluctuation in which all structures offset each other in such a way that, from a physical perspective, they added up to zero. With the Big Bang, this quantum fluctuation broke down, and particles filled with charges and forces shot into a mostly empty space. These particles later became stars, galaxies, planets, and living things like us humans. Is Gross right when he says that these particles are the answers to all the questions? Probably yes, but how do we study the behavior of particles that were in space 13.8 billion years ago? Among other things, experts use the cosmic microwave background radiation, which is considered a fairly accurate reflection of the event shortly after the Big Bang and has probably not changed much since then. However, quantum physicists and classical physicists do not exactly agree on how to interpret this imprint of the beginning of the universe. Right now, the situation in science is that quantum and particle physics cannot be reconciled with traditional cosmology. The findings from the world of shaped matter don't fit with quantum physics, or rather, the connecting link is missing. David Gross is convinced that this bridge can be found in previously unknown particles and forces. He was one of the scientists who attempted to reach a consensus between the disciplines even before the discussion set off by James Webb. As co-author of string theory and in a rational unification of quantum mechanics and general relativity, he was the first to close the gap between the two worlds and disciplines of science. Gross's work on asymptotic freedom describes how quarks behave at extremely high energies. This is key to understanding the early universe shortly after the Big Bang when energies were incredibly high. His theories can clarify currently unclear aspects of the development of the universe. However, There is some contention among scientists as the proposition of string theory is too far-fetched for many traditional physicists. David Gross suspects that the answers to all unanswered inquiries lie in the quantum fluctuations within the microwave background. The CMB fills the entire universe and can be observed in all directions around us. The Cosmic Background Explorer satellite, active from 1989 to 1993, was the first to notice tiny fluctuations in the temperature of the radiation. From 2001 to 2010, the Wilkinson Microwave Anisotropy Probe,